Hello, so in today's video here, we're going to answer question 9 from the 2021 AQA Paper 3 exam. So this question 9 is, from paper 2021, Paper 3, the AQA syllabus. And this is the final question in section A, so the pure section of the Paper 3 exam. So we're going to answer this question to get you ready for next week's Paper 3 exam. So, okay, so question 9 here. So we've got a function which is a function f, which is defined for all real values of x. So I'll just make a note here, just so we're aware that the domain of this function, so domain is x in the real numbers. So every number, every real value of x would be our domain for this one. Okay, that's our function there. And we're told that it's got two stationary points. We got one at x equals 0, and we got one at x equals minus 15 over 4. So the first question wants us to find the second derivative of this function. So we're going to start off by just differentiating the function we have to get the first derivative, so f dash of x. So bring the 4 to the front, take away 1 from the power of x, we get 4x cubed, and then plus, so bring the power of 3 to the front, so multiply by 3. 5 times 3 is 15, and then times by x, take away 1 from the power, you get that there. So that's our first derivative. So our second derivative is what we do when we differentiate it again. So multiply by the power, take away 1 from the power. 4 times 3 is 12. Take away 1 from the power, we get x power 2 there. And then plus, so again, bring the power to the front, multiply by the power, which is 2. 15 times 2 is 30. And then take away 1 from power. Well, 2 take away 1 is just 1. So we just have an x to the power 1. That's just an x there. So that's the first part done. So then the next part of the question is to determine the nature of the stationary points. Okay, so what we want to do now then is we want to plug x equals 0 and x equals minus 15 over 4 into our second derivative, and we want to see what we get. So remember that the key thing to remember is that when we want to find the nature of the stationary points, remember we've got three possibilities. So it could either be a maximum point, it could be a minimum point, or it could be a point of inflection. So we want to determine the nature, and the way we do that is we plug in our two values of x into our second derivative, and then we can determine whether we've got a maximum, a local maximum, a local minimum, or a point of inflection. So let's start with the first one then. So let's plug in x equals 0. So we're going to plug in x equals 0 into our second derivative. So if we do this, we get 12 times by 0 squared plus 30 times by 0. That's going to give us 0. Okay, so we get a second derivative there of 0. Now, that means that it's not a local maximum. So when x is 0, we don't have a maximum. We don't have a minimum. So it could be a point of inflection, but we just have to check whether for certain it is a point of inflection. Just because the second derivative is equal to 0, it actually doesn't necessarily mean that this is a point of inflection necessarily. So what we've got to do is you've got to do this test where we look at the function that we've got here. So this kind of this quartic curve, this x to the power 4 plus 5x cubed. And what we want to do is we want to think about values of x a little bit smaller than 0 and values of x a little bit bigger than 0. So x equals 0 at this second derivative here. So what we want to do is you want to consider values of x a little, sorry, let me rub this out and let me write this again. So a little smaller, a little smaller than x equals 0 and a little bigger. So the reason why we want to do this is, remember, because with the points of inflection, let me just write this over here. So points of inflection. So with the points of inflection, so for example, let's say you've got a graph like this. So you have a point of inflection here. This would be your point of inflection. Point of inflection. In order to have a point of inflection, you need to have your second derivative of this function. So this is your function f here. So let's just say that this is f of x there. So we need the second derivative. So the second derivative here must be 0. So at this specific point here, our f dash dash of x equals 0. So for a point of inflection, when you substitute that x coordinate into your second derivative, you must get 0. So we get that, that's fine. But we've got to check for x values a little bit smaller. So for like x values like here, and also for x values over here a little bit bigger than the x value there, we've got to check whether we've got a change in sign of our second derivative. So if there is a difference in sign, so if the sign of the second derivative, so if it's a positive number or a negative number there, then it must be the opposite in the red there. So let's say that when you substitute in an x value a little bit smaller than this point of inflection, this potential point of inflection, so we don't know for certain yet. If you substitute that x value in the blue region in, and you get let's say a positive number, if when you substitute in an x value in this red region, you get a negative number, you get two different signs. So therefore, it is a point of inflection. So we just got to check: does the sign of this second derivative change sign either side of this x coordinate here? So in this case, it's actually x equals 0. So actually, let me try and make this a more realistic curve. Actually, you know what? I'm just going to rub this out because I've made a real mess of this. Let's do this again. Let's rub this out. And let's try and make it a little bit more realistic. So we've got x equals 0, which is on my curve. And in fact, when we substitute in x equals 0 into our formula here, we get 0 anyway. So we could have something which looks a bit like this, I guess. Maybe let's just pretend the curve looks something like this. I mean, I know it's not a cubic graph, but let's just pretend for argument's sake. So what we want to do is you want to look at x values to the which are a little bit smaller than 0. X values which are a little bit bigger. Does f dash dash x change sign? So what we want to do, so we know that our f dash dash x is this 12x squared plus 30x. So we know that is true. So what we want to do, so we're going to consider our f dash dash x, which equals 12x squared plus 30x. So let's think about how this graph looks like. So let's think about a sketch of this quadratic graph for this f dash dash x. So we can actually just factorize out, we can factorize out a 3 in fact, and we can also factorize out an x. So we get 3x times by 4x plus 10. Okay, so we get that. So our graph is going to look something like this. We're going to have a root at x equals 0, because remember, if 3x times by 4x plus 10 equals 0, then that means we've got two possibilities. So 3x equals 0, or 4x plus 10 equals 0. So the first possibility suggests that x equals 0. The second possibility suggests that x equals minus 10 over 4, which is the same as minus 5 over 2. So we've got two roots of this graph, so this here and that there. So we've got a curve which looks like this, roughly a quadratic. So our second derivative curve, this second derivative curve looks like this. So what we can see from this graph, it's quite clear that if x is a little bit bigger than 0, then our second derivative is positive. So let's make a note of this. Again, unfortunately, with the AQA website, they don't let you write on the past papers. They won't let me write on it, so I have to use Zoom to actually write on the screen. Let me try and move everything down a little bit. There we go. That's relatively okay. Yeah, that would be fine there, I guess. And I'm just going to move this to there. There we go. Right. So we can see from the graph. So what you want to say now is you want to sketch this graph of your second derivative, and then what you want to say is we can see, so from this graph here, we can see that for x values a little bit bigger than x equals 0, so a little bigger than x equals 0, we can see that the graph is positive. So this f dash dash x graph is greater than 0. So remember, this curve here is the curve y equals f dash dash x. So y equals f dash dash of x. So we can see that for values of x a little bit bigger, we're getting positive numbers on the y-axis there. So we get positive numbers. So we've got positive sign, we got a positive second derivative when x is a little bit bigger than x equals 0. And we can also see, and we see, sorry, let me write this again. So we see for X values, I'm going to run out of room again, but let me just try and fit in as much as I can. So for X values a little smaller than, and now let me try and move my writing up. Let me try and move it. Let's try here. Okay, right. So now we can see, and if I just move the graph there, so now we can see for X values a little smaller than X equals 0. So X values a little smaller than X equals 0. We can see that F dash dash of X is negative. And again, that's because, look, if we plug in an X value a little bit smaller than 0 into our F dash dash curve, we're getting negative numbers on the y-axis, aren't we? So we've got a change of sign. So therefore, we have a change of sign. So we have change of sign either side of X equals 0. So therefore, when X equals 0, we've got a point of inflection. So when X equals 0, we have point of inflection. So yes, so a point of inflection is when your second derivative is equal to 0. So this is the first point you've got to be aware of. So the first point is that, yes, a point of inflection, you want F dash dash to be equal to 0. Yes, that's the first thing you want. And also, you want F dash dash of X to change sign. So to change, sign either side of X. So either side of the X value there. So that's your second point. So with a point of inflection, it's not enough just to do, oh, just calculate your second derivative and then plug your number in and say, oh, it equals 0. So it must be a point of inflection, because you could have a curve where your second derivative is 0, but it might not be a stationary point. So you just have got to be careful to check this second condition as well, that there is a change of sign, because if there is a change of sign of your second derivative, you can think of your second derivative as like an acceleration. So basically, if your acceleration is changing, the acceleration of your original graph is changing either side of that coordinate where you get F dash dash X equals 0, then it tells you that there's a point of inflection. It tells you that there's a stationary point. It tells you there's a point where the gradient's 0 on the curve. So we just got to be careful with that one. So yeah, we know that X equals 0 gives us a point of inflection, sorry. So that's the first point done. Now let's check the second one. So X equals minus 15 over 4. Again, I'm going to try my best to keep everything on the same page. I know this is all a bit messy, but any questions, do leave them in the comment section. So I don't want to make a mess of all this. I'm just going to rub out this domain part here. There we go. Right. So then the next thing we want to do is now substitute in our X equals minus 15 over 4. So we're going to substitute that into our second derivative, so minus 15 over 4. And when we do that, we get 12 times by minus 15 over 4 all squared, and then plus 30 times by minus 15 over 4. Let's just put that all in the calculator and let's just see what we get. So minus 15 over 4, and then square all of that, times by 12, and then so it's going to be take away 30 times 15 over 4. So when I put that in my calculator, I get 56.25. Now this is greater than 0. Okay, so when you get a second derivative greater than 0 at a stationary point, it tells you that that must be a local minimum. So therefore, because your acceleration is positive, what that basically means is that you're at the minimum of your curve. So again, if I try and do my best to explain this, but hopefully you guys understand this now, because we're not far away from the paper 3 exam. But if you do need a little bit of an explanation, if you have like a minimum point here, the reason why your second derivative is positive for a minimum point is because you're about to go upwards. So your acceleration is actually positive. So that's kind of the way that I think about it. So that means because you're again, if you've got like a positive second derivative, so again, I think about it like an acceleration. If you're accelerating at a positive acceleration, it means that your graph, if you're traveling along this curve, so you're traveling along this curve, you're about to go upwards. So now your acceleration is positive. So that's kind of the way that I think about it. So therefore, we can say that x equals minus 15/4 gives us a maximum. So gives us my bad, a minimum. Sorry, my bad, minimum. This is a minimum point, minimum. So it gives us a minimum. So minimum, if I can even fit that in, just about. So this x equals 0 gives us a point of inflection. X equals minus 15/4 gives us a minimum. I mean, technically a local minimum. That's really what we should say. We should say this word local minimum, because it's not necessarily the minimum point on the curve. So normally what we would say in maths is we call this a local. So like, as in like your local shop, we call it a local minimum. But in A-level maths, it's fine just to call it a minimum point. You're not going to lose a mark for that, but technically we say local minimum. But anyway, yeah, let's go to the next question. So I have made a real mess of this question because as I said, unfortunately AQA does not let you write on the does not yet let you edit the PDF file. And I'm just using Zoom, just being lazy and using Zoom. So unfortunately, yeah, I can't actually just annotate the page like I do with Edexcel. I'm now going to just delete everything there. Just going to delete everything on the page there. But you can scroll back if you want to rewatch that. Okay, so then part B of the question. So we want to state the range of values for which of x for which this function f of x equals x to the power 4 plus 5x cubed is an increasing function. Do you know what I'm going to do? I'm going to zoom in actually just to get more space when we do our working. Okay, so we want to state the range of values of x for which this function is an increasing function. So remember what it means for a function to be increasing. So a function is increasing. So f is increasing. Increasing with a G, if the gradient is increasing. So if the gradient f dash of x is greater than 0. So that's what it means for a function to be increasing. It just means that your gradient is positive. So if you got like a graph like this, obviously when x is between like this number there back to minus infinity, the graph is decreasing. So your gradient, your f dash, your gradient is less than 0, so it's a negative gradient. It's going down, so the graph is going down. And now in this part of the graph, when x is bigger than this like minimum point there, the graph is increasing, so our gradient is positive. So with this here, we want to basically state the range of values which this graph is increasing, this quartic graph is increasing. So, I mean, we know from the previous part of the question, so we had that x equals 0 was a point of inflection, so that gives us a point of inflection. So remember, a point of inflection is just like a flat segment of a curve. And then when x is minus 15/4, we got a local minimum. So local minimum. So, I mean, what I'm going to actually just do is try and draw like a sketch of the graph. Again, I'm going to try and make my writing a little bit smaller to get some more room. Okay, so if we think about what we've got, so we've got this x equals 0. So if we substitute in x equals 0 into the function, we got 0, didn't we? So 0, 0 is one of the corners, and this was a point of inflection. And we've also got this minimum point at x equals minus 15/4. I'm actually just going to plug this into the curve as well, just so we can get a sketch of what the curve looks like. So minus 15/4 to the power 4. I'll do this on my calculator. So minus 15/4 to the power 4 plus 5 times minus 15/4 all to the power of 3. Do that on my calculator. I get about minus 65.9. So let's just say like somewhere down there. So yeah, minus 65.9, and then this minus 15/4 there. So we've got a quartic curve. So the curve is going to look something roughly like this. So it's going to go down like that. It's going to go up like this, and then it's got this kind of inflection point there. and then it goes up like this. We kind of got a graph like that. So quartic curves normally look like W shapes like this, but because we've got a point of inflection, a flat point, remember this like flat segment of the curve here, x equals 0, it's going to like flatten off here and kind of do like a cubic shape there. So that's kind of roughly what the curve looks like. So the question wants us to find the values of x for which this function is increasing. So what we can just actually do, I mean, we could just read the graph and we could say, well, we can see from the graph. So we can see from the graph. So we can see that when x is bigger than 0, when x is bigger than 15, minus 15 over 4, we can see that the curve is increasing. So we can see that the gradient of the curve is always increasing when it's greater than this this minus 15 over 4. I mean, you've got this point here where the gradient is 0, so this point x equals 0 where the gradient is 0. So I mean, you could, if you really wanted to, I mean, they're quite lenient with this in the mark scheme. So you could either say when x is greater than minus 15 over 4, or you could say when x is so when x is greater than minus 15 over 4 and less than 0, and when x is greater than 0. So you could either say this there as your set of x values when it's increasing, or you could say that there. And in fact, instead of square brackets, I'm going to just use curly brackets for a set. So the set of x values where x is bigger than minus 15 over 4, or you can say this instead. So I mean, the reason why I'm saying this is because remember, x equals 0 here, the gradient 0, so it's not, so it's neither increasing nor decreasing, but they're quite lenient with whether you take a gradient as 0 to be increasing or not. In fact, I'm just going to actually get the mark scheme up right now. Let me just show you what the mark scheme says. Just because I think that would be a good, actually maybe that won't be a good idea because my writing is my writing is gonna supersede the screen, but let's just see what happens. Yeah, so this was the 2021 paper 3 exam question 9. Sorry that my writing again is in the way of everything, but let's just scroll down just for your sanity so you can see what they say in the mark scheme. Yeah, so with part B, they say, I mean, let me just select everything and make my writing smaller, and then we'll make it bigger again. So they say here in the mark scheme, as you can see here, that x is greater than minus 15 over 4. So they say, so this solution that we wrote there is what they say there. I mean, if we just look at the notes of the mark scheme, if there are any notes down here, no notes down here. I mean, it doesn't matter in these exams whether you are whether you do go and say, you know, x is greater than minus 15 over 4, or whether you say x is between minus 15 over 4 and 0, and also x greater than 0. You can say either one of these and it will be fine. But generally speaking, you can just it's probably just better to say that x is greater than minus 15 over 4, because generally speaking, we do include when a gradient is 0, we say that is neither increasing nor decreasing, but you can take that as increasing as well. So basically what I'm trying to say is that either one of these answers there or there would be acceptable, but hopefully, yeah, that does make sense. But please do leave a comment in the comment section if you want more clarification on that there. Technically when you do university level maths, we say strictly increasing versus strictly decreasing, because strictly increasing doesn't involve a gradient of 0, so it doesn't involve points of a gradient of 0, but increasing does. So technically speaking, a function is increasing is when the gradient is bigger than or equal to 0. So really, that's what this word increasing means. And strictly increasing, so f is strictly increasing. It's strictly increasing. That's when f the gradient is strictly bigger than 0, so with a strict greater than sign rather than the equal sign. But I mean, in A-level maths, you're not going to lose a mark if you choose either of these, basically. So again, you could either say this solution here, so x greater than minus 15 over 4, or this one here, x between minus 15 over 4 and 0, and x greater than 0. So either one would be fine. with this solution there. You could also do this without sketching the graph as well. So I want to go through a second method as well, just because you could also differentiate. Sorry, let me just rub out this line there. I've made a real mess of this question, haven't I? Let me just move this. I'm going to move it up there if that's okay. I'm just going to move this to the side up there. It's a real pain using Zoom to do these questions. Let me just go back to full screen mode if it will even let me. No, it won't even let me go to full screen mode. Anyway, right, so let's show like another way of doing this. So okay, so you could also do it like this. You could also again work out your first derivative, so differentiate it again. So when we differentiated it in the previous question, we got 4x cubed plus 15x squared. So what you can say is, well, this is going to be, you can actually draw a sketch of this curve here, and you can say, well, okay, this is a cubic curve, so factorize out the x, you get a 4x squared plus 15x. Well, actually, I'm going to factorize out another x. I factorize out the x squared. So x squared times by 4x plus 15. And then you can say, well, okay, you've got a cubic graph, which looks something like this. So your graph of your f dash of x looks like this. So you've got a repeated root x equals 0. So remember, if this equals 0, then that suggests that x squared equals 0, or 4x plus 15 equals 0. So we've got a repeated root here. So we got a repeated root x equals 0, and that's repeated because you got the squared. That root is squared, so we call it a repeated root. So repeated roots look like this on a curve. So again, they just touch the curve without passing through the curve. And then you've got a normal root. We call it a simple root. So x equals minus 15 over 4 is your other root. So minus 15 over 4, 0 there. So you've got a curve, a cubic curve, a positive cubic curve. It's going to look something like this. So touching like that, that's what the curve would look like. So we can see that f dash of x is bigger than 0 between minus 15 over 4 and 0. And also it's bigger than the gradient, the f dash x function is bigger than 0. So above the x-axis for x values bigger than 0. So again, either one of those answers. So either method gives us the same result as we had before. And yeah, so we get that as well in the mark scheme too. But again, any questions, do leave them in the comment section below, but hopefully that makes sense. So when x is bigger than minus 15 over 4, the function is increasing. Of course, we include this, we've got this point there where the gradient is 0, so technically not strictly increasing, but they're quite lenient in the mark scheme. Even though this point there is not strictly increasing, they still allow it to be trying to get the right words. It's increased. It's that they don't. It doesn't matter. I mean, it doesn't matter. You're not going to lose a mark if you say that this gradient, where the gradient there is 0, that's increasing. So you can either say this solution or that solution. Again, either solution is fine, but please do leave a comment if that did not make sense. Right, I'm going to delete all this again because again, I'm using Zoom and it won't let me go back to full screen mode. There we go. Right, so let's go down to the next part of the question. Right, so we got now a second function g, which is defined for all real values of x. So g of x equals x to the power 4 minus 5x cubed. So we want to state the single transformation that maps f onto g. So remember that our f function, so f of x was this. So f of x equals x to the power 4 take away plus 5x cubed. So we want to describe the transformation that goes from f onto g. So I mean, what do we notice? I mean, the x to the power 4 is the same as the x to the power 4 there. That's not changed. But this second term here has become negative. So how could that possibly happen? Let's think about it. I mean, if we plug into our initial function a negative x, what would happen? So if we're going to substitute in as an input negative x into our initial function, we would get minus x to the power 4 plus 5 times minus x to the power 3. And then negative x to the power 4. So negative 1 times negative 1 times negative 1 times negative 1. You actually get positive 1. So this becomes x to the power 4. And then negative x cubed. So negative 1 times negative 1 times negative 1. That's negative 1. So we're going to get negative 5x cubed here. So basically this g of x is essentially a reflection over the y-axis. So basically what's happened here is we've reflected all of the x coordinates over the y-axis. So we had before this this like quartic function like this. So look roughly like this from our sketch. And what's happened is that we've basically made all the x values negative to get our new function g. So this is our f of x there. That's our, I'll just call this f for f of x. And then our g looks something like this. So it's a reflection. So we've reflected all of our x coordinates and we get something like that. So that's our g there. So this is a reflection. So from g, from f onto g. So from f onto g, it's a reflection over the y-axis. So we're reflecting it directly over. So we're flipping it over the y-axis there. You can also say the line x equals 0 as well. So we're reflecting it over line x equals 0. Okay, so that's that would be that one. And then the next part of the question, state the range of values of x for which g is increasing. So, I mean, we can actually just use the sketch of the graph that we've got here to help us out. I mean, we could differentiate the graph again. So we could differentiate this g. And if we do that, so the derivative would be 4x cubed, take away 15x squared. And we could do like a similar technique that we did before. We could factorize this out. So g dash of x is equal to x squared times by 4x take away 15. So therefore, we're going to get 2 roots. So 2 roots, we're going to get x equals 0. That's repeated because we've got the x squared there. So x squared equals 0 implies x equals 0 is a repeated root. So that's a repeated root. And we're also going to get a simple root, a standard root of x equals 15 over 4. So yeah, our cubic derivative looks something like this. Again, I'm going to try my best to, I'm going to sketch this up here. Actually, let me just sketch this up there where I've got some space. So it's a repeated root there. And then it's a normal simple root of 15 over 4 there. So it's going to look something, so it's a positive cubic as well because you've got a positive x cubed there. So it's going to be something roughly like that. So it's a repeated root, touches there, goes down and goes through like that. So we can see that this graph is increasing when x is less than 0. So it's increasing. Sorry, my bad. Ignore that. No, that's wrong. Sorry, my bad. So the graph is, so this second derivative, sorry, this first derivative, this g dash. So it's greater than 0. It's positive. The graph here is positive when x is greater than 15 over 4. So your solution to this one is going to be x greater than 15 over 4, because when x is greater than this 15 over 4 in the graph up here, we can see that the gradient is positive because the y values on this curve are positive. So remember, when we're looking at the graph of the derivative, we're not looking at the gradient of that graph because we're thinking about the gradient of the original graph. We're just looking at the y values. Are the y values of your gradient graph positive? Yes, they are when they're bigger than 15 over 4. But for all these values down here, all these x values to the left of that, they're below or equal to 0. So with this question here, your answer would be x is greater than 15 over 4. You can also use the graphical method as well. You can look at your graph of g and you can say, okay, well, where is the gradient positive of this this g function? So it's negative, it's 0 there, but it's negative, and the gradient then becomes positive. So it becomes a positive gradient at this point there, 15 over 4, and then the gradient is positive. So now it's an increasing function. So it's increasing in this domain here. So it's increasing there. So therefore, when x is greater than 15 over 4, the function is increasing. So again, you can either look at the initial graph, the original graph of g, sketch g and say, well, the gradient is positive when x is bigger than 15 over 4. Or you can calculate the derivative like we did here, sketch the derivative graph and say, right, where are my y coordinates bigger than the x-axis? Where are they above the x-axis? So they're above the x-axis in this region here. So my gradient is positive when x is bigger than 15 over 4, because the graph y equals g dash has y coordinates bigger than 0 when x is bigger than 15 over 4. So that would be your solution there to part CI. And in fact, let's just see what the mark scheme says, just so you can see how they do it in the mark scheme. Again, my writing is all over this. But again, yeah, so they say here, x greater than 15/4, condone use of greater than or equal to sign. So again, they're quite lenient on this. They don't mind whether you use a less than sign, a greater than sign, greater than or equal to sign. As I was trying to explain before, but probably not very well, they're quite lenient on whether you include points where the gradient is 0 for an increasing or decreasing function. But if you are to study university maths, we're a lot more clearer. You know, if a function is increasing if the derivative is greater than or equal to 0, but a function is strictly increasing if the derivative is greater than 0. So if you do continue with some maths and physics, we are a lot more strict on what it means to be increasing. But in A-level maths, they're quite lenient, so you don't have to worry too much about whether for these questions you include a negative sign, a less than sign, or whether you include the equal sign in your inequality. So yeah, that would be that question there. But again, any questions, please do leave them in the comment section. Thanks a lot for watching, and again, good luck for your revision this week.